Transcranial direct current stimulation is one type of non-invasive electrical brain stimulation that is used to change the way the brain works in order to enhance cognitive performance in healthy individuals. It is currently being evaluated as treatment for multiple brain diseases. Finite element modeling, also known as FEM, is used to predict the path of current with electrical brain stimulation through the scalp and skull into the brain. Successful interventions with electrical brain stimulation require passing current through the specific task-related brain networks. The FEM modeling of the electrical brain stimulation presented here was performed at Wright State Research Institute at Wright State University in Dayton, Ohio. This work was funded by and developed in cooperation with the Air Force Research Laboratory. It was developed with standard commercial hardware and software. Electrical brain stimulation delivers electricity to the brain by placing electrodes on the scalp and connecting them to a current source. It is important that you take proper safety precautions. The electrodes shown here were developed to maximize safety and comfort during electrical brain stimulation. These electrodes were developed by Michael Wisen and colleagues and are available through Rio Grande Neurosciences. Teams of researchers at the Air Force Research Laboratory and Wright State University use them. The anode is connected to the positive pole of the battery and is typically associated with the increased excitability of the affected tissues. Here the anode is centered over the left somatosensory and motor cortices near the hand region. The cathode is connected to the negative pole of the battery and is typically associated with the decreased excitability of the affected tissues. Here the cathode is centered over the anterior pole of the right frontal lobe, sometimes referred to as the supraorbital cortex. This placement of the anode and cathode is associated with enhanced motor function or learning in multiple published studies. A typical dose of electrical brain stimulation is 1 to 2 milliamps for 10 to 30 minutes. Here we illustrate current density in the brain and surrounding tissues as the current ramps up from 0 to 2 milliamps. Here we are going to remove the scalp, then the skull, then the cerebrospinal fluid to reveal the current that enters the brain. Very little current passes through the scalp, skull, and cerebrospinal fluid into the brain. Various models indicate that between 1/50th and 1/5 of the current delivered at the scalp enters the brain. Note the scale bar on the right. In the previous display, the maximum value was 2 amps per meter squared. This display has been rescaled to a maximum value of 0.4 amps per meter squared. This change in scale magnifies the display of the current that reaches the cortex. It does not represent an increase in the amount of current being passed through the scalp from the source. By rescaling, it better illustrates the distribution and variability of current density throughout the gray matter. The described rescaling will be constant throughout the remainder of the video. The electrical brain stimulation distributes a low level of current over a wide area of cortex. The current is not uniformly distributed throughout the cortex. The highest level of current are shown with yellow and the lower levels of current with red. The regions of the brain that are stimulated depend on the location of the electrodes on the scalp. Note the subtle changes in current distribution as the anode is moved toward the top of the head and back. The electrode array can also be rotated. Rotation has less of an effect on the current distribution than the movement of the entire electrode array toward the top of the head. The diameter of the 5-electrode ring can also be changed. In this illustration, increasing and decreasing the diameter of the electrode array has a notable effect on the current distribution in the cortex. Keeping the scale of the gray matter, we will add tissue layers until we return to the scalp. First we add cerebrospinal fluid that surrounds the brain, then we add skull, and finally we arrive at the scalp. At this highly magnified scale, similar to the cortex, the current is widely distributed across the scalp. In fact, the current appears to be continuous between electrodes. This likely represents current that travels through the skin and never enters the brain. As the current is slowly decreased, the current density in the affected tissues also decreases. Finite Finally, the electrodes are removed once the electrical brain stimulation is completed and the current is completely turned off.